Gravitational field is the region around the body having mass in which the gravitational force of the body can be experienced. Hi, welcome to another video. In this video, we're going to cover gravitational field, gravitational forces, and there's no way you can talk about gravitational forces without referring to Newton's law of universal gravitation. Newton's law of universal gravitation states that any two particles of matter attracts one another with a force F, which is directly proportional to the product of their masses and inversely proportional to the square of the distances apart. So F has a direct proportional to these guys, an indirect proportion to the square of the distance. What do we mean by direct proportion? It means as you increase the force, the masses of either M1 standing alone or M2 standing alone will also increase. If you decrease the force we're talking about in terms of gravity, that's what we're talking about, then the mass of the object, the first object decreases, the mass of the second object decreases. And the same thing goes for the distance, just a tiny little bit different. When you say inverse proportion, it means as you okay, let's do it this way. As you increase the force, the square of the distance apart would also decrease. If you decrease the force, then the distance would increase and vice versa. Now, coming back to this particular diagram you have here. So these are the two bodies. They may be of the same masses, they may be of the same mass, or it could be different. Okay, it doesn't really matter at this point. Okay, so the gravitational force between M1 and M2, if you combine these two equations, is as simple as writing F equals okay, let's just say M1 M2 over R squared. Okay, now if you're to remove the sign of proportionality, we change it to equals to, and then you introduce a constant. Okay, it's called a gravitational constant, which is G, M1 M2 over R squared. All right, now what's the value of G? What's the value of G? The value of G is 6.67 times 10 raised to the power of minus 11 Newton per Newton meter squared per kg squared. Now this figure will be, since it's a constant, in questions where you need to use this figure, it will be given to you, although you have to familiarize yourself with the figure. But in case you do not remember the gravitational constant, the value, it will be given to you in questions. Now here is a question on your screen. Two spheres of masses 100 kg and 90 kg respectively have their centers separated by a distance of 1.0 meters. Calculate the magnitude of attraction between them. Okay, so based on that particular equation we talked about earlier, so let's say we represent those two masses, M1 and M2. Then the question says they have their respective centers. Okay, just one after the other, separated by a distance of 1.0 meters. So the distance between the centers is 1.0 meters settled. So distance is represented with R, 1 meter. And then the force of attraction, that's the gravitational force of attraction between them, is gm1 n2 over r squared. That was the equation we looked at earlier. Okay, so that's that on ground. Let's now list out what we have. G given from the question is 6.70 times 10 raised to the power of minus 11 Newton meters squared per kilogram squared. And then R, that's the distance, is 1.0 meters. What else do we have? The mass 1 is 100 kg, mass 2 is 90 kg. Now all we have to do is to substitute these values into this equation. It's as simple as that. So that's 6.70 times 10 raised to the power minus 11 times 100 times 90 divided by 1 squared. This will give you 6.03 times 10 raised to the power minus 7 Newton. Another question. It says a force of 200 Newton acts between two objects at a certain distance apart. The value of the force when the distance is halved is. Now let's try and interpret what this question is saying. It says that initially what we had, the force we had was 200 Newton. Now the question is asking us to calculate the final force, which we have no idea at this point. Now what happens to the distance? Initially, let's say R1, the distance is R. Initially, the distance is R, because now we have no numerical value for what R1 is, so we just give it R. And then R2, we're told that R1 is halved. Okay, R1 is R, so we can say R divided by 2. Now, what do we know? What do we know? We know that the force is indirectly proportional to the square of the distance. All right. And now, let's turn this around. Into an equation, you can say F equals 1 over R2. This one can be your constant or whatever. And if you cross multiply at this point, you will have F, let's say F1 in this case. Let's use F1. So F1 R1 squared, okay, just to have some difference, equals to 1. All right. And we can have the same expression for the second one. So the second one as well, we can say F2 R2 squared equals 1. So since these two is equal, you can say F1 R1 squared equals F2 R2 squared. All right, so let's now substitute what's F1. F1 is, you have it here, F1 is 2. Okay, let's just put it here. F1 is 200. What's R1? R1 has the value of R, so we just put R squared. And then F2, we have no idea. And then R2, we have it here, R divided by 2 squared. So from this point onwards, the only thing left for us to do is to simplify. So let's go ahead and simplify this. This is 200 times R squared equals F2. Let's open the bracket. That's R squared divided by 4. And right after that, you make F2 the subject. Okay, let's transfer 4 here. So that'll be 4 times 200 times R squared equals F2 times R squared. And then you divide both sides by R. You divide both sides by R squared. Okay, that's 200 times R squared equals F2 over R squared. Still, you have R squared cancelling R squared. You are left with F equals 4 times 200, and that's 800 newtons. So the F in this case, that's F2. Let's just make corrections to that.